presentation. And next we have the electronics category finalist, AI deep learning and low-cost passive RF wireless vibratory strain sensors. Representing the team today is Ramon Soto. All right, welcome.
Hi, good afternoon, everyone. I'm Ramon Soto, and I'm really excited to be here all the way from Daytona Beach, Florida. So it's a little cold right now for me being here in New York. But I would love to just kind of share with you about, our journey with Sensatek. And I like to first kind of start out with the story. So I started my career in the Marine Corps, which today, by the way, is my birthday. I am 248 years old. It's the Marine Corps birthday. That's like the new holiday before Veterans Day. And also, it is the birthday of Sensatek. So, while in the Marine Corps, I was in the reserves. I studied, got a degree in physics at Florida A&M University while in the reserves, and learned that there wasn't much I can do with a degree in physics in the Marine Corps. So after I was done with my contract, I moved down to Daytona Beach, Florida, and pursued a lifelong passion, the aerospace industry, and I pursued a master's in aeronautics at Embry-Riddle. And it was here where I was also, as my colleague, did research on jet engines, and we were working in the jet engine lab. We had some GE engines in there and some Pratt engines, and we're working on some new propulsion systems. And we had parts that kept failing at high temperatures, and no one really knew why. And so, the Marine side of me kind of kicked back in again, and I wanted to further investigate this problem, wanted to be a problem solver. So I went out, started talking to the engine manufacturers like GE and Siemens Energy, and I've learned that, we weren't the only ones who were having issues with temperatures or quantifying what's going on in the most critical parts, such as the rotating blades. And so I went out and found that utilities also use jet engines to generate power called aeroderivatives, except when their engine basically was failing, they were forcing $3 million outages per occurrence for a new set of blades, because they were having to operate the engines much differently with renewables coming online. You now have more frequent stops and starts that causes the blades to creep. But also, we were talking with others, since we're recording, I won't say who it was, other folks on oil and gas platforms who were using gas turbines and compressors on LNG platforms also had blades come off, and it forced a $300 million outage. You can see the press release with that. So I decided to, so Sensatek was founded to attack these problems, and we used some research that came out of the university system. So Sensatek was formed to license technology that came out of the universities to prevent these machines from exploding. And by doing that, we can increase safety and also reduce the operations and maintenance costs associated with maintaining these systems. And so I invented a sensor that basically uses an antenna as a wireless temperature sensor, depending on the material system, and a wireless strain gauge for dynamic strain monitoring. So you can see here, this is just a very crude model, but our IP covers the ability to use an antenna as a sensor. So for temperature monitoring, the dielectric constant of the material changes linearly over the temperature range, and so there's a relationship between the resonant frequency and a dielectric constant. So by wirelessly measuring the resonant frequency, we're able to know what the temperature is in real time. And then on a material system that is strain dependent, the sensor, the antenna it changes its radiation pattern based on its geometry, and we can get the wireless dynamic, we can get the strain reading, and we oversample it to get the dynamic strain, which we then convert to vibratory frequencies. And so we went out back to those OEMs and the power producers, and we were able to demonstrate our sensors on helicopter engines. You can see the sensor on a rotating blade, on a stationary antenna, communicating with the sensor that's spinning 22,000 RPM at over 1,000 degrees centigrade. We put our sensors on large gas turbines with Siemens and Duke Energy on grid-connected engines, and also were used on hybrid electric propulsion systems. And what we discovered was that the OEMs and the utilities weren't as incentivized as we had thought to really address the issue with solving the multi-million dollars in blade failures. And so we had to do like any good startup does, is we had to pivot. And so we then, we were in the Next Era 35 Mules program. They're a large wind fleet owner and power producer. And we had team members that said, look, I know that you were putting this on gas turbine engines, but we're not going to ever put this on all of our engines because we're in a regulated space, and we're just really not that incentivized to eliminate those failures. They like the CapEx things. And but they were like, but on the unregulated side with our large wind fleet, we have issues with we're really putting the money there. We're in the unregulated space. We're responsible for the revenue loss and for the CapEx associated with blade failures. So as the wind turbine space, they're growing at a rate of 8% year over year, but for the large fleet owners like NextEra and Invenergy, they're growing at a rate of 20% year over year. But blade failures are continuing to plague the industry to the tune of $2.4 billion a year. And that is the size of the GDP of Aruba. And so based on our customer discovery, we learned that depending on if you're an offshore or onshore wind turbine, that blade can range anywhere from a $350,000 per occurrence to a $900,000 per occurrence if it didn't take out the entire $2 to $4 million machine. And 7,000 of these blades are happening every year, and we're going to see that problem as blades start to get larger to increase efficiencies. The OEMs are just trying to really get them out there, and so we're seeing a lot more issues with blade failures. And so drones are great. But they are also prone to misses because a lot of the cracks are barely visible, and where the blade becomes catastrophic is seen from the inside of the blade due to delamination and lightning strikes. Well, that's where we come in. We put our antenna, our antenna sensor, the size of a pizza box, taking our small sensor and making it much larger to now monitor what they call the kill zone within the blade. And so what we're looking at is the strain, which we're then converting to vibration. And as cracks form, as there's damage on the blades across the fleet, the software would then tell them how the vibration of the blade differs across the entire fleet. So we have 4 issued patents on that technology. This is the cartoon version of it, so shameless plug. I kind of already sold this thing to Siemens Energy, making them think that we already had this ready to go. And so we don't, so I would use that money to actually build it and to sell it to them. And who we have in our pipeline includes Invenergy from our relationship in the M-Hub Accelerator in Chicago, and NextEra and Constellation. With just their fleet alone, we can save $1 billion per year across a fleet of 32,000 wind turbines. And that's not it. We're working with other oil and gas companies who came, like Williams, OneOak, and also Constellation, and said, look, can we also use your sensors to monitor leaks on reciprocators if we know that a combustor isn't firing properly? Of course, in good old founder fashion, it's like, absolutely, we're experts at that. And so they are on our roadmap, but we're first focused on the wind turbine space. And as we get those use cases, because it seems like it takes a village to raise a child, it also takes one to raise a business and to make a sale. So we're going to use the use case from the wind turbines to also use that in other applications like aerospace and oil and gas. And so it takes an individual to make a difference, but a team to win a championship. But we're very lean. We have PhDs in electrical engineering. Some of us have also came from working with the OEM before at Siemens. And also we have participated in many energy-related accelerators that helped us understand the voice of the customer, going out to the site, learning their pains and gains to influence our roadmap. So I'm Ramon Soto, and I approve this message.
Any questions?
I'd like to know if your sensors, the strain and temperature sensor, are they combined or are they separate?
Yes, sir. Great question. They are separate. We did research on 80 different material systems to determine what is the best temperature sensor that doesn't change as it relates to strain, and so that became our best temperature sensor. And then vice versa for the strain sensor, which one did not change? It kept its dielectric constant relatively the same, so that it's only measuring strain. But it can be in the same package, but they're two different systems, two different sensors. Thank you. Thank you. Yes, sir.
Yeah, you touched on a very interesting point through my career, which is vibration measurement. And that sensor, and mainly I see it is going on very high frequency devices, like either it is turbines, whether air turbine or gas turbine or aircraft engine. Now, does that sensor, when it measures, what does it measure? Frequency and amplitude, or just frequency?
Great question. So initially on the wind turbines, what makes our sensor good compared to like accelerometers and vibration sensors is that for composites, we're initially focused at the lower frequency, so anything less than 100 hertz. And so we're really good at that with the larger sensor size. But while working also with, an example here. So while working with like Pratt, for instance, or other OEMs, they want, the higher frequency stuff. And so with that, we're being compared to tip timing. So we put multiple antennas in different locations so that we can get the frequency and the mode at that particular time. So it's like they're asking, hey, if I get the frequency of the blade at the higher frequencies, because it changes its frequency from 0 to 360, and so the question is, where at in that chart did you have that frequency? And so that's what we're collaborating with the OEMs on. And so right now, the higher frequency stuff, we're aiming for 100,000 hertz, which is 100 kilohertz. We're not there yet, but it is on our roadmap. But the wind turbine, family, they were like, oh, we want to buy this right now. And the OEMs were like, hey, we just want to kind of study this to death, and then we'll think about using it. So it's on our roadmap, but it's not a key priority just yet. But good question. Thank you.
Thanks for the presentation. You mentioned that it's the size of a pizza box, but it's not as thick as a pizza box. I'm thinking about aerodynamics of the wind turbine. Is there any issues there?
Right, great question. So our sensors vary in size depending on the application. So we've made really small ones, the size of a postage stamp to a ladybug, and we've also made some the size of a sheet of paper. But the thickness is less than 0.1 millimeters in thickness. And so it's similar to what you would use like a Kapton, mask or a Rogers material. And the sensors are mounted initially on the inside of the blade for blade root delamination. So we're essentially catching what the drones aren't catching. We are thinking about, applying it on the outside of the blade, like closer to the tip. But most of the insurance claims are coming from the kill zone and the blade root. So it seems like that is probably the best place to start on the inside of the blade.
One last question.
Sorry to keep you stood up there. What's the frequency with which blade failures actually occur?
That is $1 million question. So on a wind turbine, since we're being recorded, on a wind turbine, maybe the natural frequency is around 8 to 9 hertz. So we're anticipating that as the blade starts to crack or as it starts to delaminate, that it's going to lower the frequency. But just to make sure that we catch other failure modes that we're not aware of, because the customers, the fleet owners, they don't really, there's an educational piece where we have to help lead them on that, but we're capturing between 0 to 150 hertz so that we can compare what they're seeing on the drone data and on the human-based inspections to what we're also seeing on the vibrations. So with that pilot with Siemens, we're hoping to better understand that correlation and how the failure modes, how it changes the vibratory frequency.
Can I ask a quick follow-up?
Please.
How often do blade failures occur?
With one customer that we're talking to right now, they had 40 last year, so it was about $16 million bill, and they're anticipating more to happen. But also, it's not just the blade failures. When they identified a Category 3 or Category 4 crack, they're now having to do 6 drone inspections instead of only doing 1 drone inspection. And it's now increasing the operations and maintenance costs on the project, and they have to lock up that amount of money for like 5 years based on how they financed the project. So where we come in, not only are we catching blade failures, but it's also eliminating the amount of drone inspections that have to be done. And when you do a drone inspection, you got to shut the machine down. You got to coordinate that. There's more eyeballs on it. There's more O&M involved on it. And they're losing revenue when it's down by doing an inspection. And so it's twofold, reducing the O&M and also mitigating blade root failure. But one customer had 40, not all customers, but one had 40 blade failures. The average fleet is about 10,000 turbines. Thank you.
Thank you.
Thank you.